Good morning. My name is Patera from University of Warsaw, and I would like to present to you the results of our research which I conducted together with Jacek Matulewski from the Nicolaus Copernicus University in Toruń. The topic of our presentation is comparison of three dwell-time based gaze text entry methods. At the beginning, I would like to present three types of gaze keyboards which were the explanatory variable in the hypothesis we considered. Gaze text entry (GTE) with use of visual keyboard displayed on computer screen is an important topic for both the scientists dealing with the gaze interaction and potential users, maybe people with physical disabilities and their families. The most commonly used technique for GTE is based on dwell time regions at which the user needs to look longer to activate the associated action, in our case, entering the letter. On this slide, you can see two types of gaze keyboards. On the left side, you can see the standard gaze keyboard based on dwell time regions with QWERTY layout. On the right side, you can see the molecular keyboard in which the buttons change their size. So, keyboard on the right side is a dynamic keyboard. Keyboard on the left side is a static keyboard. The keyboard with dynamic elements named molecular was designed in our lab in order to improve the standard keyboard by adding some dynamic features helping to find the most probably letters, namely the increase of the size of the buttons containing letters selected using an algorithm. On this slide you can see two-step keyboard in which the group of letters is selected first and the particular letter may be chosen in the second step. In the experiment took part 29 healthy persons, 13 males and 16 females in age between 21 and 30. Respondents now have previous experience in GTE or gaze-controlled software. All respondents were asked to enter 5 pseudo-sentences boiled with 3 words, each from the Polish dictionary, that were also used for the letters and words suggestion algorithms. This was repeated for each keyboard type. The order of testing the gaze keyboards was randomly chosen for all participants before the experiment. During the experiment, the eye movement data was recorded, as well as the list of entered and removed letters with their timestamps. It allowed us to calculate the temporary and average text entry rate, as well as to determine the total time of task execution and calculate the number of errors. We treat these values as objective measures of GTE method's usability. In addition, subjects were asked to fill the SUS questionnaire. It's not obvious to indicate the measure of GTE method's efficiency. One should take into account all their functionality and features. This one may count the number of inputs, which may include the correctly and incorrectly entered letters and/or its removals, uses of Alt key and buttons for a grab of letters in case of two-step keyboard. It is also possible to count errors, long pauses, or measure the time of performing the task, or even calculate the rate of entering the correct text or just the rate of entering the correct letters. However, taking into account the ultimate goal of gaze keyboards, which is enabling the communication by gaze interaction, we decided to use the average input speed, which equals the number of all input events, not only the letters, divided by the total time of entering the correct text, which is necessary to complete the task, including also time of incorrect inputs and its corrections. Therefore, such calculated values takes into account the time reduction associated with using suggestions as well as the increase of time caused by various mistakes. Such definite average input rates for all gaze keyboard types are presented on this slide. The so-called standard keyboard is clearly fastest, but the two-step keyboard and the molecular one do not stand out so much. Notice that the total time of text entry, which is supposed to be twice larger for two-step keyboard size, it is requires double dwell time acceptance, is of the same order of magnitude for all GTE methods. Similarly, for the total number of inputs, the value for two-step keyboard is not the largest. On this slide, you can see charts about errors during use gaze keyboards. By errors, we mean above the single typos, which we recognize by single use of the backspace key as well as the late noticed mistakes, which lead to repeated use of the backspace key. The surprising result may be that the largest number of errors were also made in case of standard keyboard with the well-known covered layout. Notice that it is much lower in case of non-standard keyboards. The possible explanation for this is that for most of the respondents, the transfer or skills from the physical keyboard operated by fingers to the gaze keyboard displayed on the screen occurred. Thus, these users had no problem with finding the keys, so they accelerated and, as a result, made more mistakes because they controlled their eyes moves less carefully. The results of the SOS questionnaire show that usability of the standard keyboard was best rated by respondents. 80 points in 0 to 100 point scale, and the two-step keyboard was judged only a little worse, 77.2 points, while the molecular keyboard came out significantly worse, 58.9 points. In addition, one can split the SAS results into two factors, usability and learnability. The molecular keyboards is still the worst at both. 53.4 for usability and 80.1 points for learnability. But it seems that while it is difficult to use, it is not difficult to learn. It also seems interesting to compare examined keyboards, considering how difficult it is to, after launching, finding the right button and in particular to start entering the required text. We have used two oculometric indicators to examine this. The time to first fixation at the area of button corresponding to the first letter in the text the subject is supposed to enter and its duration. However, we took into account only standard and molecular keyboard since the two-step keyboard differs from the other two. Time to first fixation, which indicates the difficulty of finding the right object, is significantly shorter for the standard keyboard than for the molecular one. This may be due to the fact that the buttons layout of the standard keyboard is well known, and the molecular keyboard, with round buttons which change sizes and positions even if the change of the letter is only slight. It's more confusing. In turn, first fixation duration reports for how long the subject had to look at the button to make sure that persons found the right one. Again, it's much longer for molecular keyboard. We also checked some standard quantities characterizing eye movement, fixations and saccades average duration and scan path length. Statistical tests did not confirm that they differentiated various gaze keyboards. However, one can note that the longest fixation duration and shortest saccade duration was obtained for a standard keyboard, while the shortest fixation duration and the longest saccade duration was obtained for a two-step keyboard. This may indicate that the latter keyboard requires the user to search longer for the right keys. In opposite, in case of the keyboard with standard buttons layout, searching was faster and more efficient. It is confirmed by average scan path length measured during completion of the single tasks, which is longest for two-step keyboard almost by 30%. We have also checked the usage of word suggesting mechanism. It was used in more than 50% of cases of entered words, but there are no important differences in use of this mechanism for various gaze keyboards. Moreover, we noticed that the strategy of some subjects during the experiment, especially in case of standard keyboard, which consisted in the use of the word suggesting mechanism in order to complete the current word, even if there was no exact match with the required word, and then to change its ending. Notice that the difference may be also due to the overconfidence in use of standard keyboard, which more often causes the use of suggestions and the need to corrections of incorrect entries. However, this hypothesis is not supported by the total number of suggestions, which is the lowest for the standard keyboard. Okay, let's go to the summary of our research. First of all, say it about aim our experiment. The aim of the experiment was to check the usability of the modification of standard gaze keyboard. Adding the dimical elements to the keyboard with QWERTY button layout activated with dwell time. We hoped that changing the size of buttons with suggested letters will help writing by gaze. Even though this graphical interface changes are some distraction for users. In addition, we wanted to compare these two keyboards with the two-step keyboard, which allow one for gaze text entry with less precise control of A movements. So, the standard keyboard remains significantly easier to use, taking into account both objective and subjective usability measures. It seems that even a relatively small disorder of the QWERTY layout, as one introduced to molecular keyboard, causes confusion of users, which leads to a decrease in typing rate and the user's comfort. The sense of confidence that accompanies the use of a standard keyboard also leads to many more errors. Eliminating these errors could significantly increase the rate at which individuals use this keyboard.